This is Physics 2211 Lab 4 Oscillations. So an introduction. The purpose of this lab is to compare the motion observed in our video to the motion predicted by GlowScript's computational model. We then want to plot the change in kinetic energy, the change in gravitational potential energy, and the change in spring potential energy, and finally, the total change of energy of the system on a graph against time. This system includes the spring mass system plus the Earth. Surroundings don't include anything. And a preview of our results is that we found that the system's total energy stays at zero, which is per the energy principle that energy cannot be created or destroyed, but the individual energies, kinetic, gravitational potential, and spring, do change as time goes on. So let's talk about our principles. Newton's second law states that net external force equals change in momentum of a system over time. Now, this is important because we're basically going to use this definition to derive the velocity update formula, which we're going to use later, and also the position update formula. And another thing we have to keep in mind is the energy principle, which states that the change in energy is the work done on the system plus the heat transfer due to the change in temperature. And we're going to be assuming that there's no work done on the system and no heat transfer, meaning the change in energy should be zero. So this is our observed motion. This is our video on the left, a graph of our results. And as you can see, this is the change over time. For the X, this is the X graph, and then below would be the Y graph. So let's talk about our computational model. First of all, we state our initial conditions. We've got the ball mass, the initial position, and the initial vector. And this is to match the observations when we took our video in the tracker app. We then state some pretty basic things, the gravitational force, or surface, spring constant, and the relaxed length, all of which we match to our video. And then we can see that here we put in the energy formulas to define the initial kinetic, the initial gravitational, and the initial spring energy. And all of those added together is just the initial total energy. So here's a continued. This is our loop, which is basically going to model what happens while the ball is in, while the system is in motion. And here we have force formulas, which we've seen before. And you add together the net force on the system is obviously going to be the gravitational force plus the spring force, nothing else. And they're obviously going to and then here we have the velocity position and the update formulas, which we derived before using Newton's second law, as stated. And here are the change in energies for, we have kinetic, followed by gravitational, followed by spring. And of course, the change in total energy is going to be the change of all three of those added together. So here's our result. As we can see, there's a difference between the model and the experiment. And as you can see, the experiment seems to kind of approach its position faster, takes less time to do so, suggesting that there's a force in the actual model, kind of, which we, from the video, there's a force acting against motion, which is slowing it down somewhat. And we're going to explain what that is. It's the drag force. So let's talk about possible errors. One, the center of mass is not selected properly in tracker analysis. Well, yeah, this is just human error, as in when you're selecting the tracker, you have to click on the center of mass. If you're off by a couple of, pixels, that can affect it, not by a lot. So the bigger, most probable cause is external forces acting on systems such as drag or friction, mean that the system is not isolated. So actually, when we talk about our energy equation, that's false. Work is actually done on the system in the form of a drag or friction force. And that's why you see that the position is kind of delayed as compared to the time if we go back a slide. And that's because there's a force acting against this motion, which is drag or friction. So does the model and observed motion follow the energy principle? So since we assume no work is done on the system and there's no heat transfer, the total energy, which is the orange line, stays at zero. However, the kinetic, gravitational, and spring energies are constantly changing. And note that at any point, the total energy will add up to zero, right? So if we take this point, right? Boom, 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 adds up to zero. Anywhere you look, it's always going to add up to zero. So let's talk about the X and Y period of oscillations. Using the graph, we can estimate the period of oscillation for the x-axis is 1.6 seconds, while the period of oscillation for the y-axis is 1.5 seconds. And the 0.1 second difference could be due to failing to find the precise center of mass, like, in each frame of the spring mass system, or the camera angle the video was recording.